Perfect. Hello, I'm here to present the efforts of the JAMLL team. This team consists of 5 members, Joe, Anto, Matt, Leo, and myself, Leonardo. This team is focused on modeling efforts for the ISIC 2024 skin cancer detection with 3D TBP competition on Kaggle. Next slide. So this is just our video consent that we consent to share this video, and this is a list of acronyms that will be addressed in the presentation. Feel free to always come back to this if you ever need to reference them. So the focus of the ISIC skin cancer detection competition is a classification problem with the goal of identifying skin cancer and whether a lesion is benign or malignant. This image classification comes from the ability to take these total body photos, TBPs, and do automated cropping and scanning for the lesions on these total body photos. The goal was to take the characteristics that have been pulled out of these images, some metadata, and the images themselves to make a model that can predict whether or not these lesions are malignant or benign. And this is to help doctors more quickly diagnose the many patients that they would normally have to see and be able to do scanning of the whole body in a much quicker process. So the goal is to have a model that can, with very high success rates, make these predictions. Next slide. The test train and hardware specifications of the competition were built on focusing using the Kaggle editor online to write and process the model. The given data was a set of 401,000 images, and associated with that was a table of metadata that was extracted from those images with 55 features for each associated to each image. In addition to the data set that was given, we were allowed to include outside data if that helped improve our model. And the training equipment that was authorized was a GPU or TPU with up to 15 gigabytes of capabilities and RAM up to 12.7 gigabytes. The total model time has to be less than 12 hours runtime, which is easy to compete to, and the final submission is just uploaded to the Kaggle website as a submission.csv of the outputs of the model. Next slide. So for the competition, the scoring is based on the partial area under the curve, or the receiver operating characteristics of our model. And very specifically, since this is based on kind of a medical imaging, and you kind of want to have that good high success rate instead of just lots of classifications, the partial area on the curve has to be above the 80% mark. So that means that the scores are set in these ranges of 0 to 0.2, which is that partial area under the curve area. So as long as our true positive rate, as shown here, is above that 80% mark, then it's accepted into the competition, and those are the rankings for the leaderboard. So the true positive rate is determined by taking the true positives and dividing it by the sum of the true positives plus the false negatives. Having that above that 80% mark is what we're looking for to get on the leaderboard in this competition. Next slide. There's a efficiency prize that's also given to the top-rated performers on the previous metric, and this efficiency prize is just based on whoever has the highest score above the benchmark and with the fastest runtime. As you can see below, the efficiency is determined by the partial area under the curve, divided by kind of a normalization of the benchmark over the max partial area under the curve, plus the total runtime of the notebook divided by 43,200 seconds, which is their kind of standard limit of the 12 hours of GPU time. So this is just a secondary prize. Currently, our team has submitted multiple times throughout the week to try and improve our scores. As you can see, we managed to get up to a 0.155 on the leaderboard and slowly creep our way higher as we tried many different variations of the model and tweaking of hyperparameters, as the changing of the scores is only between 0 and 0.2. Small increments of 0.001 are quite a difference on the leaderboard. Now, what we did find is, as we went over this challenge for the past few weeks, many people continued to join the competition, and in fact, the competition size more than doubled in the last few weeks. So even with our slowly increasing score, we found ourselves creeping a little bit lower on the leaderboard, sadly, but we are trying our best to crawl up as much as we can. And I'm going to hand this off to our next team member.
Thanks, Leonardo. Yeah, so I'll be talking about the key features that we use for the model. So before I dive into or feature selection, I kind of want to talk about or provide a bit more background on the metadata that we ended up using. So as we mentioned earlier, the data set is essentially a set of images. It's about 40,000 plus of them, but they also have a corresponding like CSV tabular type of data format, which contains all different descriptions of the images that were collected. So inside of this metadata, there is two sets of this similar data. One of them is used for training, which contains basically everything that we ended up using for the model. And then we have the verification data set, which is more or less the same data, but it has about 11 less features than the training data. We noticed that the reason for this is because in the training data, if any of the images was flagged as malignant or a positive, then there is a few more features that correspond to the description of, why, or I guess describing the malignant characteristics of that specific image. So that's why the training data set has a bit more features than the actual verification data set. Since the verification data set, we don't really know if it's malignant or not. So the other thing that we found a lot of relevance in once we looked into the features is any data that related to what it's labeled as the total body photography. Um, Essentially, there is different descriptions of the images that go into the size, the color, the location, and so on. So around 33 of these features are the ones that we had the most interest on and ended up working the best for our model. The other thing to mention is the heavy data imbalance that we have once we looked into the data set. So we have over 40,000 images that are essentially negative, and only 393 that are positive. So this data imbalance was something that we really had to kind of work with and struggled a little bit to kind of get going at the beginning. But then once we were able to realize this, we, utilizing the different features and so on, we were a bit more successful. Next data set, please, or next slide, please. Awesome. So this is just a brief example of a little subset of those 33 features that we mentioned earlier. So every image basically has this corresponding feature description. And as you can see in there, they can be, if you're not too familiar with, I guess, the medical terminology, it can be a little confusing, but it goes into everything from the area to the perimeter, the smallest basically lesion diameter, and so on. It really is very granular data that gets described and collected for every single one of the images. Next slide, please. So this is just another subsample of, say, another part of those 33 features. So as you can see, all of this data set was actually, it's based on a histopathology assessment that were both done by a professional, a medical professional, and also part of the AI, like image recognition part. There is not really a citation on how exactly they did this, but this is all we know based on what the competition provided. Next slide. So now that once we started to kind of take a look into what are the most important features for our model, what you're seeing in here in this image is we basically just did like a feature importance using a random forest. And this is kind of like a snippet of the 15 most important features. All in all, in reality, we found best to use all 33 features that correspond to that tabular body photography data set. Because the more we started reducing the ones that were quote unquote not as important, it didn't really affect the model. But if we took too many of those out, it actually affected the model in a negative way. So we ended up keeping most of those. Next slide, please. So now when we go into the actual pre-processing steps that we utilize for the dataset, as just to reiterate one more time, we only used the tabular or metadata that corresponds to the images for our final model. So the flow kind of goes in a way of importing the data set, then we essentially drop any columns that did not correspond. There is no overlap between the training data and the verification data. As I mentioned, the training data has 55 features. The verification data has, I think, 44 or so. So anything that's not in that overlap, basically, we drop since we're not going to be able to have it for the verification data set. And then we dropped other columns that essentially just we didn't really find any relevance. So some of those were like the ID, the source of the data, copyright info, in and so on. The other thing that we added into the flow was one hot encode for the categorical data. So what we did is there was this one feature that actually corresponded to the location of where the image was taken. So it was what we did is we basically took this one feature and expanded it into multiple sub features, as you can see in the table below it, right? So anything that had the word, head or neck got a one, or left arm got, a one, and so on. So how we achieved this is we looked into that feature. We did like a unique extraction of all the unique words that were used to describe the locations, and then we just kind of extrapolated that into this matrix and used one hotkey encoding. So other things that or other methods that we could have done um, was doing like feature scaling, which didn't really provide any better results than what we had. The other thing is like trying to deal with the data imbalance. We looked into downsampling the negative samples. Since we had so many negatives, over 40,000 of them, we figured why not take just a small portion of that and train it. The other thing was to replace any nulls or nands with the median instead of leaving them blank or completely or just removing them. But none of these approaches really improved our final model once we tried them out and tested them out. So now I'm going to hand it over to the next person.
So we tried various modeling techniques such as applying XGBoost, CapBoost, random forest classifier, and logistic regression. We realized that our latest model that resulted in the best score on the training metadata dataset so far has been CapBoost. CapBoost is an algorithm that allows for gradient boosting on decision trees and provides an improved accuracy and reduction in overfitting in our dataset. It supports both the numerical and categorical features, has built-in automatic feature scaling and cross-validation, achieves good results without much hyperparameter tuning, and has an extensive set of experimentation. However, applying techniques such as grid search may allow for discovering an optimal set of hyperparameters for the CapBoost model. Some key differences we realized in our modeling techniques between CapBoost, XGBoost are that CapBoost has auto-categorical feature handling, and it does not require preprocessing due to built-in preprocessors and scalars, and has symmetric tree splitting techniques, whereas XGBoost requires preprocessing such as one-hot encoding due to issues with categorical features and uses depthwise tree splitting. Next slide, please. This is a sample model from one paper that we found, and it structures the CapBoost model that we decided to use. Some of the key features, again, to reiterate about the CapBoost model, is that it has built-in handling for categorical features, has excellent results without any parameter tuning, has built-in methods for handling missing values, automatic feature scaling. It's robust to overfitting, and it has built-in cross-validation, as well as it's fast and scalable on a GPU. Some common applications that CapBoost model can be used for are classification tasks, regression tasks, ranking, or other recommendation systems. And some limitations that we've seen with CapBoost are memory consumption, training time, hyperparameter tuning. Sometimes it may have issues with supporting large-scale distributed training, and it has a significant amount of documentation for applying various modeling and hyperparameter tuning techniques. Next, please. And below is a pipeline example of our pre-processing steps and modeling training with the hyperparameters shown. Each step of the process can be seen in the final model verification, which is done with a ROC curve and a confusion matrix. Some of the pre-processing steps were one-hot encoding. It's dropping features with minimal data points, matching any training metadata to the test metadata, and then filling any of the non-applicable datums with unique values. Transitioning then to our modeling approach, we, as discussed, use CapBoost classifier with about 3,000 iterations. We reduced our learning rate to about 0.005. We had a model depth of 7, a random speed about 0, as well as we had about 10 early stopping rounds as our limit. We also tried to use various test and train splits, anywhere from 75 to 25%. And we had various learning and testing parameters with a total runtime of about 1 minute, 25 seconds. In terms of our verification, we use the confusion matrix with benign and malignant models, with benign and malignant results as shown, and an ROC curve with an AUC score. Next slide, please.
Great. I guess I can take it from here. So as mentioned, CatBoost was our main model that we experimented with, and at least I should say the main one that gave us the best results for the metadata. So here, as Matt was describing, we have the ROC plot for the CatBoost model. This is just one snapshot of our collected data and inferences. So you could see the true positive rate when it's above 0.8, above 80%, I should say. You could see that the area under the curve is 0.1531 in this case. So this is a great example of how we evaluated our model's performance. In other words, if we got results that were lower compared to this 0.153 value, then we determined that that was a bad tuning. So if we were, for example, tuning hyperparameters or experimenting with different sizes of data sets or trying different models instead of only submitting to Kaggle, this was a way for us to verify how our model was doing. Next slide, please. And in addition, so the competition used the ROC, that the score that was mentioned earlier. But in addition, we also use the confusion matrix to kind of double verify for further verification of our results. So here we could see how CatBoost classifies it pretty well overall. So it identified correctly 72 out of 84. So in other words, 85.7% of the malignant samples, and also 87.7% correctly identified with the benign samples. So obviously there's room for improvement, but this was another way, as mentioned, the main purpose here was to see how the model was doing instead of just looking at the ROC plots. So for example, in some cases, we observed that these percentages really dropped or were not as good, and that was another way to confirm the performance of the model. Next slide, please. Okay, so in addition to everything we mentioned, we also tried some other models. Obviously, again, the CatBoost was our main one. These were just a few other ones that we experimented with. So XGBoost, LightGBM, his gradient boosting classifier, and what happened was with XGBoost, we got a score that was still pretty good, 0.154, not as good as the CatBoost model. Like GBM, we did not submit that one because, as mentioned, when we were evaluating the ROC plot scores, it gave us such a low score that we didn't even bother submitting, which saved us submissions and obviously was better. Same thing with his gradient boosting classifier. And finally, we tried another voting ensemble, which technically gave us really good results, but we suspected that it overfit the results. The ensembling model we used consisted of the XGB classifier and the CatBoost classifier. So obviously, as expected, when we submitted to Kaggle, it resulted in a very bad score. So a classic case of overfitting. We didn't address it at this time, given the time that we had, but this would be something that we'd obviously want to improve in the future. Next slide, please. Okay, so just to kind of circle back on the imbalancing of the data set to provide kind of a visual example here. Some of the things we tried in our pre-processing stage is to use different balances of the training data. So on the left here, we have the original distribution with all of the samples. And on the right, you could see that when we cut the sample of the benign samples to 10,000, so that really reduced that specific sample set. And then you could see that the balance starts to appear. It just seems more balanced overall. And we tried different ratios. We made them almost equal in some cases and tried going the other way. But all in all, none of them improved the final results. Basically, what we found was that using all of the data, so the more data we provided to the model training, it always gave us the best scores. Perhaps there is another way to generate more of the malignant cases, perhaps by the mean, and like increase the data set that way. That's one thing we didn't get to try. Would be interesting to see how that would affect the score. But as of now, again, our final model used all of the provided data sets. Next slide, please. I'll hand it over to the next presenter.
Yeah, okay. So as we mentioned earlier, in addition to the data that we used for our final model, there was also image data provided, which was effectively just JPEGs of different skin samples, and they were labeled benign or malignant. So when we first set out to attack this project, we had the goal of kind of making a model with the metadata and then also making a model with the image data, and then hopefully putting those two models together to sort of use all the provided data to ideally get the best prediction. The image processing effort was fairly difficult, largely due to the fact that we were constrained to using Kaggle notebooks, which were prone to lagging and even stalling out and crashing completely. But we are going to talk about the image-based efforts a little bit. So by the end of the project, we were able to get a very simple image processing model together, just a simple convolutional neural network with a couple convolutional layers and a couple max pooling layers. But so we were able to get this pipeline together and run inference on the provided test images, which was about 3 images. But when we tried to submit this, the submission actually stalled out on the test set. It exceeded the 12-hour runtime. So there's obviously some inefficiencies with our pipeline there. But given that we got here by the end of the competition, we also sought to see what other models were out there that have been submitted already that maybe we could leverage to use this image data. So we did find a few models that worked pretty much out of the box. One of them that worked was this ensemble method that used both the metadata and the image data. And what it effectively did was took the image data, run some augmentations on it, like flips and rotations, and then it fed that data into 2 different pre-trained image processing convolutional neural networks, one called EfficientNet and one called EVA02. I have the links for those below. And then what it did is basically took the output predictions from those 2 models and it added those as features to the metadata that we used for our main model. And then it combined all that data and fed it into a CatBoost, which was the model that we ended up going with as well. The score for this model was one of the higher scores we saw, 0.172. Ultimately, we found this model pretty late in the game, and the implementation was a little too complex to make any actual meaningful changes to it that would have impacted the score. So we're not saying this is our final model, but it was quite insightful to see that you could combine both the image data and the metadata to get a better score. And then I'll hand it off to Matthew to kind of close out on these efforts.
So another modeling technique and solution that we attempted to look at is taking a notebook that uses both tabular and image data and concatenates the 2 image sets using a multi-input concatenated deep neural network and convolutional neural network model. And here we use both the tabular and the image input data. We perform the tabular pre-processing, such as dropping the columns with more than 10% of non-applicable or non-unique data sets. Trying to drop any columns that have any uninformative data. Try to impute the mean and numerical data and then impute the most frequent categorical data. Try to do one-hot encoding and categorical data and robustly scaled and numerical data, as well as we want to normalize any confidence score on the nervous column. In terms of the image pre-processing, we would resize the images and try to normalize them to grayscale between 0 and 1 in order to later on use a sigmoid output. We want to crop the image and the tabular data to the same length by its cardinality and then combine both of the data sets. Looked at adding optional layers to the models that would allow data augmentation on the images, such as randomly flipping the images, rotating the images, or zooming the images in and out. This augmentation technique would allow for more variance in the per epoch in the training scheme. Then we would try to combine both of the tabular and the image pre-processing techniques into a combined pre-processing step. Here we would sort all the tabular data by the image data labels and keys, and then crop both the tabular and image data sets by the minimum length or the minimum cardinality of those 2 data sets. And then we would combine and batch both the image and the tabular data, and then split the combined data sets for training, validation, and for tests. And below are some of the links provided to the key performing notebooks. Next slide, please. The modeling approach to the multi-input DNN-CNN concatenation model has both a tabular modeling section and an image modeling section. So after preprocessing for the tabular modeling, we would load the tabular data into 4 hidden dense net layers, and they would be sized in reverse from 64 neurons to 512 neurons. And here we use ReLU activation functions. There were optional batch normalization, dropout, and L1, L2 generalization norms that could have been added to each of the dense net layers. However, I decided not to apply those. In terms of the image modeling, I decided to use the Keras ResNet 50v2 backbone convolutional neural network. It was pre-trained already on the ImageNet dataset. The input to the CNN would be just the image data, and the output of the convolutional neural network would be flattened to add an extra channel or an extra dimension to the batch dataset. Afterwards, the output of the 4 hidden dense layer networks that would process the tabular data and the output of the CNN network that would process the image data would be concatenated together to a concatenated model. We would then run those combined, we would then run the data through combined layers. One layer would be a ReLU hidden layer followed by a final sigmoid output layer. For the model for the model compilation, I applied an atom optimizer with Nestera momentum to adaptively change the learning rate. And a key feature to the concatenated model is that at first there would be a pre-training and a post-training step, and in the pre-training step, I would lock all the convolutional layers except for the last convolutional block. I would pre-train with a coarse learning rate of about 0.001, followed by unlocking all the convolutional layers and post-training with either the same or a finer learning rate. And I found that using the same coarse learning rate would generalize the learning of the model. Both the pre-training and the post-training were done with 3 epochs each, with a significant length added to each training epoch. That would be about 3 times the length of the tabular dataset. I experimented with various CNN model, and the table here gives the performance matrix for some of these models. The baseline notebook that's provided in the source link used the efficiency net v2b0, and it scored about a base score of 0.0139. One thing that I noticed wrong with that model was that it wasn't seeded properly, and simply by seeding it and using the default coarse tuning technique, I was able to improve that score to 0.146. And then I experimented with a potentially larger CNN model that had slightly more parameters. and I applied the pre-training and post-training fine-tuning technique, but I didn't yield better results. And then finally, I used the ResNet 50 v2 CNN model where I applied both the pre-training and post-training fine-tuning techniques, and I increased the number of epochs to 3 from the baseline 2, and I was able to significantly improve my accuracy score from my baseline to 0.152. And we think that this was a very interesting solution that combined both the tabular and the image data sets, although it did not beat our original CapBoost model. Next slide, please.
All right, and that's it. Thanks for listening.